Hi everyone, let's solve this question. This is another database system, the complete book by Ullman exercise question. Okay, so this question you can find in this book. Okay, let's solve it. So in this question, a relation is given to you. Relation A, B, C, D, E, 5 attributes are there, and this is decomposed into 3 relations. So this is a non-binary decomposition because we have 3 sub-relations A, B, C, B, C, D, A, C, E. For each of the following FD set, so these are the set of functional dependencies that are given to you. Use the chase algorithm. So this chase algorithm we have to apply, and we have to check whether the decomposition is lossless or not. Okay, and also in this question he is asking whether the dependencies are preserved or not. So let's solve each of these questions. Let's try to solve it. So okay, so let's solve this first part. So let's solve. So I can say part A. Okay, in this part A you can notice that this relation A, B, C, D, E, and these are the decomposition, and these are the functional dependencies that are given to you in the part A. B determines E, B determines E, and you can notice that CE determines A. Okay, so this is the set of functional dependencies. Again, you can very simply you can apply the chase test. So the chase algorithm you can apply. So we have total 5 attributes A, B, C, D, E. These are the 5 attributes that we have. Okay, so let me just quickly do it. So we have total three sub relations R1, R2, R3. So these are the sub relations that we have. Okay, so these are the sub relations R1, R2, R3. And now what we can do, we can fill the entries. You can notice, so R1 means ABC, R2 means BCD, and R3 means ACE. Okay, so ABC, so we can put entries here. Then you can notice BCD, so we can put entries here. And you can notice ACE, so we can put entries here. Okay, this is the initial situation. Now what you can do, you can now you can, okay, very simple. So we can notice that whenever B, so B implies C. What it means that if two tuples have same B value, they must also have same E value. So you can notice these two tuples have same B value. So these two tuples must also have same E value. So here we can put the same value because we don't know what is the value of E. So let me put value B here. Okay, so this is what we got. So this is what we got. Now what we can do? Okay, after this what we can do? Okay, so from this, now you can notice again that this dependency, look at this dependency, CE determines A. What it means that if two tuples have same CE value, CE combination. So if two tuples have same CE combination, you can notice these two tuples, they have same CE combination. So this tuple have same CE combination, and this tuple also have same. So you can notice these two tuples, they have same CE combination. Then A value also must be same. So two tuples have same CE value, then A value also must be same. So in these two tuples, A value also must be same. So what we can do, finally I can say that this A we got here. Okay, correct. Okay, now what we can see, again you can okay, so can we do something now? So again B determines E. So because B determines E, so in these two values B value is same. So in these two tuples C value must be same, which is already same, no problem. So we cannot do anything right now. And you can notice CE determines A. So in these two tuples CE value is same. In the first and second tuple CE value is same, and in the first two tuple A value is also same. So we cannot do anything now. Now it will not change. You can notice now it will not change. Okay, so finally I can say that now this will not change. Okay, so this will not change. Actually I can say that this is what we got, and now this data will actually not change, correct? So finally I can say that this is what we got. Now whatever you do, this will not change, the entries will not change. So now no change, now then no change, now no change possible, now no change possible. Okay, and you can notice we don't have any row with all A entries. So there is no row with all A entries, with all A entries. So what we can do, so this is a lossy, so this is a lossy decomposition. So this option A, this is what we have done. Okay, so for this, in this question, for this option A we have done. Okay, so this is a lossy decomposition. Let me also do the whether this is dependency preserving decomposition or not. So let me also check it. So you can notice let me check it whether this is dependency preserving decomposition or not. So let's see the dependency preservation or not. Okay, now this is the set of functional dependencies, and what is our decomposition? Our decomposition is like this: we have a b c, we have c b c d, and also we have a c e. Okay, so this is our decomposition: a b c b c d a c. Now here what will happen? So what are the functional dependencies which are only applicable on these three attributes? Okay, so just find out. So okay, what is the FD set? What is the FD set of R1? Means those functional dependencies which are applicable only on ABC. So what are those which are applicable only on ABC? You can notice that B can determine E, but B cannot determine anything else. So here actually there is no non-trivial dependency. You can just check it out that in this A, B, C, you can very easily see that there is no non-trivial functional dependency here. Okay, so in this example I can say that in this relation R1 there is no non-trivial functional dependency. There is no non-trivial functional dependency. There is no non-trivial functional dependency. Okay, let's see for the relation R2 what are the set of functional dependencies. So you can notice what are the functional dependencies which are applicable on these attributes B, C, D. Okay, now again you can notice that B can determine E, but okay, we cannot do anything else. So again here also no non-trivial functional dependencies, you can check it. And you can notice R3 what are the functional dependencies which are applicable on this relation R3 on these attributes A, C, E. So you can notice that CE can determine A. So this is applicable. CE can determine A. Nothing else is applicable. So finally I can say this is okay. Now you can notice this is F1, F2, F3. Now just tell me, this is the question. Can I say F1 union F2 union F3? Can I say this will, okay, just ask yourself, okay, that will it cover F? Will it cover F? Will it cover F? F1 union F2 union F3. You can notice in F1 there is no non-trivial functional dependency. In F2 also there is no non-trivial functional dependency. So only this non-trivial functional dependency we have. So we can cover this. This is already covered here, but you can notice we cannot cover this. This B determines E. This cannot be covered. Okay. So actually I can say that this B determines E. B determines E is not covered by F1 union F2 union F3, is not covered by F1 union F2 union F3. So I can say this is not dependency preserving decomposition. So this decomposition is not a dependency preserving decomposition. Okay, so this is how you can solve this question. We have already seen that this for option A, this is not dependency preserving decomposition. Also this is lossless. So I can say for option A, what I can say, option A, this is lossy. This decomposition is lossy also. So the decomposition is lossless in option A, that is lossy. This decomposition is lossy also, and this decomposition is non-dependency preserving. The dependency is also not preserved. Okay, so this is the answer. Now let us check it out. Option B. Okay, so this is what we have done. Now let's see what is option B. Okay, so in option B, AC determines E, BC determines D. Okay, so this is the option B. What option B is saying? So let's see option B. Option B is saying that AC determines E and BC determines D. Okay, so this is the option A that is given to us. You can notice AC determines E, BC determines D. BC determines D. Okay. Now, what are the relations? Again, you can notice these are the sub relations. We have ABC, we have ABCD, and we have ACE. So these are the sub relations that we have. Now let us check it out. First of all, is this dependency preserving or not? So this is what we need to check. So let's check whether this is dependency preserving or not. So in this relation R1, what are the functional dependencies that we have? So you can notice what are the functional dependencies which are applicable on A, B, C, only on these attributes. What are the functional dependencies which are applicable? Okay, so here you can notice that what AC can determine, AC cannot determine anything, and AC can determine E, but what are the functional dependencies which are applicable on A, B, C? So again, there is no non-trivial functional dependency. So here also I can say there is no non-trivial functional dependency. There is no non-trivial functional dependency in this relation R1. And what about R2? Okay, so in these, for this, okay, BCD, what are the functional dependencies which are applicable only on B comma C comma D? So you can notice BC implies D. This is applicable. And finally, I can say what are the functional dependencies which are applicable on R3? So ACE. So what are the functional dependencies which are applicable? That is ACE. Now you can notice that F1 union F2 union F3 will cover F. So this is our set of functional dependencies F, and you can notice this dependency is covered here, and you can notice this dependency is covered here. So finally, I can say that F1 union F2 union F3, okay, covers, this will cover, this covers F. So this is a dependency preserving decomposition. So this decomposition is actually dependency preserving. Okay, this option B, the functional dependency set that is given to us in the option B. So for that we will get dependency preserving decomposition. Now let us check whether we have lossless decomposition or not. So let's check this. Okay, so what we will do here, again we will apply the chase algorithm we will apply. So let me apply the chase algorithm here. So you can notice ABC, BCD and ACE. These are the relations that we have. So let's apply the chase algorithm. So again there will be A, B, C, D, E. These are our attributes. Again what you will do, you will create the table. So you can notice this is R1, this is R2, this is R3. So what we have here, okay, so you can notice we have, here we have that, okay, so here we have ABC. So this will be entry A. Here we have BCD. So here will be entry this, and here we have ACE. So these will be the entries. This is the initial setup. After this initial setup, now let's see what we can do. You can notice that AC determines E. So this AC, whenever you can notice in these first row and second row, you can notice this combination. So in the first row and the third row, okay, first and third row, you can notice that the value of AC is same. So the value of E also must be same in the first and third row. Okay, so here I can say that, okay, in this row and in this row, the value of this must be same. So what I can say, that this will be A. This is what we got. Now what we can do, okay, after this what we can do, so again you can notice that BC determines D. BC determines D. Okay, so because BC determines D, you can notice here BC value, here BC value is the same. In the first and second row, you can notice that BC value is same. So the D value also must be same in this row. So okay, so in this row, okay, what should happen? The D value also must be same. So this is what we got. We got A here. This is what we got. And now we can stop because we got a row with all the A values. This is what we got. This is a row with all A entries, I can say, with all A entries. So this is where we can stop. Okay, and because of this row I can say that this is a lossless. So this option B, you can notice this option B, question option B, this option B decomposition, if you notice, or I can say the option, in the option B, the set of functional dependency that is given to you, okay, with respect to that we are getting lossless, we are getting lossless, also we are getting dependency preserving decomposition. Okay, so this decomposition we are getting. So our decomposition, remember decomposition is same, but with respect to functional dependencies, in option B, we have different set of functional dependencies. So for the, with respect to the functional dependencies that are given in option B, our decomposition is actually lossless, comma, dependency preserving decomposition. Okay. Now similarly, you can try the other questions. Okay. Let's see option C now. In the option C, this is the set of functional dependencies that is given to us. Now again what we will check, let's check whether dependency preservation decomposition is it is dependency preservation or not. Okay, so the relation R1, the sub relation R1 has three attributes ABC. So what are the functional dependencies that are applicable on these attributes? Okay, so you can notice ABC. So A can determine D, D can determine E. So you can notice between these attributes, what are the functional dependencies that are applicable between these attributes. So A can determine D, D can determine E, and similarly you can notice B can determine D, D can determine E. So actually again here okay, between these attributes there is no non-trivial functional dependency. So here also we can say that there is no non-trivial functional dependency in this relation R1. Okay, so for these three attributes there is no non-trivial functional dependency that we have. Now let's see the relation R2. For this relation R2, you can notice what are the functional dependencies that are applicable. So we can notice that B can determine D, D can determine E, that is fine. But you can notice B can determine D, and what else do we have? Okay, so you can notice D can determine E, nothing else. So I think this is the, yes, this is the only functional dependency that will hold on these attributes. Now R3 means ACE. So what are the functional dependencies that are applicable on these attributes ACE? So we can notice A can determine E because A can determine D, D can determine E. So A can determine E. Okay, and you can notice nothing else. So this is the only functional dependency that we have. Now we can notice in this F1 there is no non-trivial functional dependency. In F2 we have this dependency. In F3 we have this dependency. Now just find out, okay, the union of F1, union F2, union F3, will it cover all the functional dependencies in this F? So this is our set of functional dependencies. Will F1 union F2 union F3 will cover F? So you can notice this functional dependency is covered here, and we can notice this function A depends okay, I can say, so this, I can say this dependency is covered. Actually this dependency is also covered. So this A determines E, this is also covered. But you can notice that A determines D, that is not covered. So actually this dependency is not covered by this F1 union F2 union F3, and D determines E, that is also not covered. So I can say that this is what I can say: F1 union F2 union F3 not cover. Okay, they do not cover A determines D, this is not covered, and D determines E, this is not covered. So I can say that this is a non dependency preserving decomposition. So this decomposition, I can say the decomposition is same, but the functional dependency set is different now in the option C. In all these options, you can notice the functional dependency set is different. So with respect to the functional dependency set that is given in option C, I can say that the decomposition is a non-dependency preserving decomposition. Okay. Now let's check it out. Is it lossless? So what we will do, we will just apply the algorithm that we have. Okay, so the chase algorithm we are going to apply. So this is A, B, C, D, E, these are the attributes. The same thing we will do. Okay, the columns will correspond to the attributes and the rows will correspond to the relations R1, R2, R3. Now what you can do, okay, so here what you can do is again ABC. So this entry we will do. In R2 we have BCD, so these entry we will do. In R3 we have three attributes ACE, so these entries we will do. So this is the initial setup. Now after this initial setup, what you can do, okay, so this is the initial setup. Now you can notice A determines D. Okay, A determines D. So because A determines D, what I can say, you can notice because A determines D, what I can do here, because A determines D, so in these two rows A value is same, so in these two rows D value also must be same. In this row D value also must be same, so I can put BB. So this is what we got here. I can say, okay, so this is what we got here, we got BB. Okay, so this is what we got. Now what we can do, so after this you can notice that D determines E. Okay, so D determines E. So in these two rows D value is same, so in these two rows E value also must be same, so basically this must be A. Okay, so finally I can say that this will be A. Now what we can do, okay, so after this what you can do, you can notice that okay, so after this B determines D, so B determines D means in these two rows B value is same, so in these two rows D value also must be same, so basically we can put it A, because remember we are interested in the A entries, we are only interested in the A entries. Okay, so no other entries. Okay, so we are only interested in the A entries. So finally what we have this, I can say we have A here, we have A here, and now I can say that what we can do, now we can stop because we have a row with all the A entries. So this is a row with all A entries, so here we can stop, and I can say that this is lossless. So this is where you can stop and you can say lossless. So option A, This option C. In this option C, the set of functional dependency that is given to you with respect to those functional dependencies, the decomposition is actually lossless. So the decomposition is lossless but non-dependency preserving. So the decomposition is lossless but non-dependency preserving decomposition. So remember, decomposition is same. Your decomposition is not changing, but with respect to the given set of functional dependencies, I can say that our decomposition is lossless and also non-dependency preserving. Okay, so this is how you can do option C. Now we will see option D. So this is the option D. Now let's see option D. Okay, now A determines D, CD determines E, E determines D. Again, first we will check whether the decomposition is dependency preserving decomposition or not. So the relation R1 means ABC. So what are the functional dependencies which are applicable only on these attributes? So those functional dependencies which are applicable only on these attributes A, B, C. Okay, what are those functional dependencies? You can notice that A can determine D. Okay, and so nothing else I can say. A can determine D, but and then you can notice CD can determine. So again here I can say there is no non-trivial functional dependency. There is no non-trivial functional dependency in this relation R1. In the relation R2, which is BCD, what do we have? So the set of functional dependencies which are applicable only on these attributes BCD. Okay, so you can notice CD determines E, E determines D, CD determines E, and E determines D. So CD determines D, that is a trivial dependency. So we don't worry about the trivial dependency. Okay, can we determine something else? So you can notice we cannot determine B, we cannot determine C, and can we determine D? CD determine D, that is a trivial dependency. Again, there is a no non-trivial functional dependency that we have here. Correct? Now, what is R3? R3 means ACE. So what are the set of functional dependencies that is applicable on R3? Okay, so that is ACE. So A can determine, you can notice A can determine only D, nothing else. And C cannot determine anything else. E can determine D, nothing else we can do. Okay, and you can notice, so whatever you do, again here also no non-trivial functional dependency. So you can check it out. So finally I can say that F1, F2, F3, they don't have any non-trivial functional dependency. So definitely this is also not covered, this is also not covered, this is also not covered. None of the functional dependencies is covered. So I can say that F1 union F2 union F3 does not cover, this does not cover any, I can say any non-trivial FD, any non-trivial FD. It does not cover any non-trivial FD of F. So finally I can say that because of this situation I can say this decomposition is not dependency preserving. So this decomposition is non-dependency preserving decomposition. Okay, so this is the point. Now let's see whether this decomposition is with respect to this set of functional dependency, our decomposition is lossless or not. Again, the same method you will apply the chase algorithm A, B, C, D, E. This is what you are going to get. So just create a table, and in this table you can notice the columns correspond to the attributes and the rows will correspond to the relations. Now what you are going to do? So here you can notice this is ABC. So these entries you will put. This is BCD. So these entries you will put, and this is ACE. So these entries you will put. Now, okay. Now after this you can notice A determines D. What it means that if two rows have same A value, then they must have same D value. So these two rows must have same D value. And you can notice E determines D. Okay, so you can notice E determines D. So if two, but here you can notice E does not have same value in two tuples. Okay, now you can notice CD determines. Okay, so this is what we got. What we got is this point. So I can say that this is B, this is B. Now what we can get? Now you can notice that CD determines E, and you can notice in these two rows CD value is the same. So in these two rows I can say E value must also be same. So this must be A. So this is what we got here. I can say that this A we got here. Now E determines D. Now you can take E determines D. So now what you can do? So this E determines D. In these two rows E value is same. So in these two rows, D value also must be same, which is already same. This is already same. So can we do any changes? Okay, let me see. So can we do any? Okay, so okay, now you can notice A determines D. Because of this A determines D, what you can do? So in these two rows, A value is same. So in these two rows, D value also must be same, which is already same. Okay, and now let's see the last. CD determines E. So in these two rows, CD value is same. You can notice in these two rows, CD value is the same. So in these two rows, E value must be same, which is already same. So we cannot change. You can see that now nothing will change. No change will happen. So finally, here I can say that no change will happen. Now no change will happen. And you can notice no change will happen, and there is no row. I can say there is no row with all A entries. There is no row with all A entries. So because there is no row with all A entries, so I can say that this is a low C. Okay, so this option with respect to the functional dependencies that are given in option D, I can say that our decomposition is low C, also non-dependency preserving. Okay, so the decomposition that we have, this decomposition, with the decomposition is same, but with respect to the set of functional dependencies that is given in option D, I can say our decomposition is actually lossy, also non-dependency preserving. Okay, so this is the answer. Okay, so this is how you can solve this question. So this is a question from the book Ullman. Okay, you can find it in the second edition of database by Ullman book. Okay, and we have already done all the four options. We have seen in each option, we have seen whether the decomposition is lossless or lossy. We have also seen whether the decomposition is dependency preserving or not dependency preserving. Okay, okay.